So let me start a bit unusually. Let me start with just formulating the result. And then our goal will be to understand the notions in this result and hopefully some ideas of the proof. So the proof is a bit technical. It follows a known strategy. However, there are some small improvements here and there. So I don't expect that we can go through the full proof, though okay, we'll see where we are. So what is this theorem? And I'll formulate it in a very provocative way. So just as the title, strong RSW estimates or Ising model on basis embeddings. Okay, right now you didn't learn anything. And my idea is that actually this part of the blackboard is not visible where the title is, even though the line is there. I suspect that the title is not visible to those who are following us through Zoom. Okay, so let us first start with this notion. What is a strong RSW? So I'll be defining Ising model and S embeddings later, and I will try to explain why we care. So what is a strong RSW result? We saw RSW results and usual RSW theory last week in the class of Ian. So strong RSW tells that if I have a quad, and this quad can be whatever you can imagine, just a quad in the plane. And for a while, I invite you to think about the square grids. Models are defined on the square grid. So if I mark 4 points at the boundary, like A, B, C, D, and I ask about crossings that touch the boundary with unfavorable boundary conditions. So my colors are yellow and red, following suggestion, Trishen suggestion rather than yellow and blue. So I ask about crossings from boundary to boundary with unfavorable boundary conditions. And I want the probability of such crossings is uniformly bounded from below, provided that the extremal length between the two arcs, which are the A and BC in this domain, is bounded from above, provided they're not far away from each other. So if you never heard about the extremal length, just think about this plane made out of just sheet of steel, and you measure conductance between two guys. Or better, extremal length is not the conductance, it's resistance, provided that they're not far from each other, then the crossing probability is positive. So the advantage, and that's a kind of most universal way of formulating these results, the advantage is that this notion is very robust. So it is stable under conformal maps, which is already good if you want to prove some whatever convergence results. And also, like if you're in a graph, you quite often can say that the extremal length on the graph, which is exactly the resistance, is comparable with the continuous. Extremal length also up to a constant. So that's just the most general form of the RSW theory if you want to have interfaces of yellow color touching the unfavorite boundary conditions. Okay? So that's RSW result. Now, it's known that to prove this result, and that's in the work of Goswami or a seminal work, roughly, no, it's later. I apologize, I forgot to check the year. So it's called proper scaling. It's about scaling relations and properties of the RAF interfaces in FKQ. So to prove what is the year of that? 2020. Okay, yeah, thank you. It could have been in 12 here. Thank you. It's known that actually what you can prove you can deduce the statement from the following. Imagine that you consider all domains. So for these domains, you say that they are centered. If the ball of radius are belongs to domain if there is a boundary. And I'll be introducing right now some constants here instead of 2. So C naught will be big constant. In their paper, this is just 2 or 3. Does not belong to the domain, which means that, okay, here is my box of size R. And then I insist that there is a part of the boundary which is roughly at the same distance to that. But the domain can be much worse. Like it can be just a single slit coming from here. So that's also a clear domain. And then very, very, very far away somewhere else. And then for such domains, what you want to prove? You want to prove that the probability that this box, let me just abbreviate it, BR, is connected, yellow connected to the boundary inside. Also, not to very far removed boundary, so it will be like the same order of magnitude. Is at least. Well, the passage from here to there is actually has little to do with the discrete machinery. And the point is that, okay, intuitively you have a roughly similar state. So you want to find crossings of that kind that touch unfavored boundary conditions without any assumptions about this boundary. So you should think that this boundary is actually very, very irregular. And the typical usage of this theorem, so why do we care? Well, the typical usage of that is when you want to promote, say, convergence of interfaces to the convergence of loop ensembles. Because if you think about all interfaces in your model, then, and by the way, this Ising, this is FK. To say so, that's percolation model. But that's not for the spin Ising, that's percolation model. So when you want to promote convergence of single interfaces to the convergence of loop ensembles, you need somehow just observe your loops one by one, and you need to understand in which order you glue them to each other. And this allows you to estimate, bad events, to rule out bad events. So out from here, you can immediately prove that, say, the 6-arm exponent is strictly greater than 2 and things like that. So that's just a useful tool. So, and then if you already know that your interfaces converge to Celia 6 1/3, then you can play further if you wish. So from here, you can say that for the spin Ising model, you can deduce that quantities, spin correlations normalized by 1-arm events, they also converge to CFT predictions. Then it's a separate question how you figure out this normalization, but at least up to 1-arm normalization, you have much more. So the role of this statement is that, at least in the current presentation, in the way how we think about these models up to now, this is an important technical block. Even though it looks a bit boring as it is, right? Why at all do we care about such a generality? It plays an important technical role in this development. Okay. So up to now, I believe that I explained what strong RSW is, though I haven't explained what FK Ising model on S embeddings is. So I explained what kind of statement I want to have, and I didn't give you this definition. So the second part is here, what are S embeddings? Oh, this is a relatively natural framework to study an Ising model on. And to have a link with the mini course that happened last week, S embeddings play the same role for the Ising model as T embeddings play for dynamics. So you can either think that already a certain grid is drawn in the plane, or you can also think that somebody gave you a model and then you try to find a representation of this model, combinatorial model in the plane. So formally, what you have just tilings by tangential quads. So here is my notation. So this is a tangential quad. And this is the center of the circle. So these two guys belong to the graph. So those are vertices, say V and V prime. And these guys belong to the dual graph, U and U prime. So you think about the Ising model defined, say, on faces of the original graph with certain interaction constants and the domain walls representation. Or you can think about the model defined on these and then consider high temperature expansion. This model, this will be the same width. So, okay, this is a tiling of them. So right now, probably it's not very clear why should we care. Why we should care. Okay, so why this is not a totally absurd notion. There are particular cases of this stuff. I haven't defined what the interaction parameters are yet. I'll do this in a second, but I want to start with some particular cases. Rhombic tilings. So rhombic tilings is what we briefly saw in Ian's class. So this means that all these tangential quads, they're just rhombi. And let me right here with critical the invariant widths. Wait for a second about for the discussion. So, but that's exactly the model that Ian mentioned under the umbrella of universality. So that's a particular example. Another important example is that any critical doubly periodic Ising model admits a canonical S embedding, admits periodic. So this is a very restrictive class. If I just give you a model defined on a doubly periodic graph with certain interactions tuned so that the model is critical, then you cannot typically represent it on rhombic lattices. So you can always represent it in this way. And then you can play with many other things, like you can re-embed massive model, say, on Z2 or something like that. So you can start with the Ising model on Z2, which is slightly off critical, and then you can represent it in this way. You can re-embed the graph in this way under the relational landscape.
Just to check, when you say massive model, you mean when you have an external field, or you mean with?
No, there is no external field. Okay. Sorry. No, there is no external field. So this is massive in terms of temperature. So this means that I'm slightly off critical. Oh, that's temperature perturbation. Or in the same vein, you can play with random setups. You can start with Z2, for instance, with tiny random interaction constants near the critical point, and again, try to re-embed it in this way. So Remy Mahfouz has a paper on this. So here the logic is that of these examples is that you start with a model defined maybe on a nice graph. So this W periodic could have been even Z2, but with non-homogeneous weights, W periodic. And then you try to represent it in this way. And in some cases it is done, it can be done. And this story about this embeddings can be viewed as a story of giving a tool which does not depend on the concrete setup, like which can be applied to many different setups and kind of produces this technical result simultaneously, all of them. So up to now, I defined the combinatorics. And by the way, if you want a link with T embeddings of the last week, then this is also a bipartite tiling of the plane if you do this way. I will not expand on that, but with each Ising model, there is a bipartite dimer model associated, also called combinatorial Bayesianization procedure. That bipartite dimer model admits subspecial T embeddings, and here they are. So that's really a particular case of that. Okay, so up to now I defined combinatorics, but I didn't tell you what are the Ising weights. So that's now the point. And the first observation, just, I don't know, may I say here, open your chakra. This is actually a three-dimensional picture. Probably you do not see it right now. So why is that? So that's actually what I'm drawing, the tilings by tangential quads. They should be viewed as surfaces in the three-dimensional space. So what is the algorithm here? So first, let me also be slightly more pedantic and say that those are not vertices of my graph, but they are positions in the complex plane. So my S takes my graph and its dual and sends it to the complex plane, right? So my graph, it lives somewhere in the other room, and this is a fully combinatorial object. And here I'm trying to represent in the complex plane in a special way. So given such a picture, what I can do, I can define the third coordinate following the rule here. Following the rule, so it will be a real coordinate. And the rule is that UV minus QU by definition is SV minus SV. If I have a tangential quad, then the sum of these two lengths is the same as the sum of those two lengths, right? By the way, that quads are not assumed to be convex. They can be non-convex as well. And then say, think about definition of being tangential, this identity. Or there is a circle that touches lines. And so there is this identity, and this allows you to lift this quad to define the third coordinate consistently. So the image of each concrete quad will be something like that. With these 2 points being B is in my notation, and these 2 points being. So that's a three-dimensional picture. Now, let me tell you what are the weights of the Ising model here. So the weights of the Ising model. With every edge of my graph, I associate a number. So this number, let me call it XE. I prefer to work with spins sitting on faces of the graph rather than on vertices of the graph. So in more standard terminology with classical direction constants, that's the rule. That's the price to pay for two different spins at u and u prime being disaligned. Okay? And I use parameterization tangent 1/2 theta e for these guys. I'll comment in a second on this rhombic tilings example. So let me proceed with the definition, but I'll comment in a second with this rhombic tilings example. And then geometrically, so that's just nothing because, I mean, in each equality, there is a new variable, right? That's a very useful way of defining things because you have one more variable in each new expression, and this holds automatically. So now the link with the geometry is that if I take the ratio of these two lengths measured in the space R to 1, then it has something to do with theta. What I'm writing is just the length in R to 1, right? And altogether. So those are just distances in R to 1. So as it is, it looks a bit weird and would have been completely unexpected if we didn't have this embedding story with R to 2. But yet again, so this is a particular case. If you start folding this tiling over edges, then you will get exactly, you will see immediately that one of the coordinates degenerates. And maybe two important comments is that first, this is invariant with respect to isometries of R to 1. And you can see, I mean, why this is a natural notion somehow similarly to what I explained for dimers. And an example, which is too simple, of course, but when you start with rhombic tilings, then when lifting this rhombus.
Just to check, it's tan PT or tan half?
This is tan theta e. Here is 1/2.
Okay.
And here is what it is. Yeah. And when you start with rhombic tilings, then basically you have two white guys at the same height. You go up, down, but these guys are at the same height. These guys also at the same height. And what happens is that you just measure distances in the plane. And my bad. It's other way around. Oh, okay, other way around. Use upstairs, use downstairs. Again. Oh, then here, theta e is just this. Well, I'm very bad in remembering who is theta and who is pi over 2 minus theta. So that's just, this should fit the standard rhombic tilings picture. Yeah, other way around. Oh, minus 1/2. That's a good idea. I didn't get it first. Even 0. Okay, so that's the model. Yet again, I don't want to motivate this model too much. For me, say already, this doubly periodic class is a good example. Let me say that for doubly periodic case, this is a subcase of things with bounded geometry, and strong RSW is independently proven by Remy Mafouf last year. It's a different technique because here that's a flat case. So for doubly periodic story, the surface is above the scale of a fundamental domain is just horizontal, and this simplifies things. Okay, so that's the model. Now maybe I should say what the bounded geometry is. And the bounded geometry is simply this simply means that all edges are comparable. All angles are bounded away from 0 and to uniformly bounded. So there are some small constants such that the squads, they do not have tiny angles, and all the edges are comparable with each other.
What does all edges are comparable with each other mean? It means
Again?
like the distances, the edges are comparable. Does it mean like
all edges are comparable to each other with some absolute constants? Like there is a constant 100 such that the ratio of any two lengths is smaller than 100. And the same here, so there is a constant 1% such that all angles are at least 1%. Yeah. So, okay, now we do have, and I defined what are the interaction constants for the Ising model. So if you want a definition for FK percolation, then for FK percolation, if you should instead specify what the probability to have an open edge is. And the answer is that is 1 minus tangent 1/2. I believe it's correct. And that's again this passage to theta star is because my model is defined faces rather than this. So that's the result. This result applies to many classes of Ising models just through this embedded procedure. And maybe that's a good point to ask about the questions. Are there any questions? Because then I'll try to list some ingredients of the book.
no question?
Okay, let us go forward. So maybe even before listing ingredients, let me just make a remark on RSW in the Ising case. I'll just warm up. Usual RSW. What is the usual RSW? Usual RSW is existence of circuits with unfavorable boundary conditions. The minimal statement you need to prove for that is that if you have rectangles, say with self-dual boundary conditions, and you ask about probability to have a crossing with self-dual boundary conditions, so if these probabilities are bounded from below, then there is a standard argument that do it. So here the point is that in many, when you speak about percolations, when you are speaking about percolation, for instance, boundary conditions do not play any role. And because of that, you just say, oh, okay, I have a crossing from left to right. And when you're speaking about these dependent models, then boundary conditions do play a role. And you ask yourself what kind of the color which color you should have at the left, red or yellow. And the point is that having yellow is already enough. So this is a standard argument from some old paper by Hugo Gabortetti and Crystal Garman.
Yeah, so in your circuit, is there free boundary conditions on the inner annulus as well? Or is
Oh yeah, I changed the colors here. Sorry, yeah, that's unfavorable boundary conditions everywhere. So I'll let it be the other way around. So this is unfavorable here and here, red. And I'm wondering about yellow circles. So they are with the opposite. So the intermediate statement, if you kind of so happen that you don't know the statement, the intermediate statement is that you prove that in a rectangle with all unfavorable boundary conditions, there are crossings from middle to middle. And once you are here, you can simply combine for rectangles as usual. So, okay, that's just a percolation type argument. Now, what makes the Ising model special? So in the Ising case, one can use fermionic observables to prove this. And here I want to discuss or to hint from where the contradiction comes. So the fermionic observables, this is much more rigid structure than parafermionic observables for other models. So the fermionic observables FZ, which are discrete holomorphic functions. And there are many, okay, maybe not tons, but several definitions thereof. So you can come to the ear just classically starting from spin disorder formalism of the Ising model, or you can use a more modern definition of stats, defining them through sums over interfaces, and combinatorially that's just the same, because spin disorder correlations, they simply have the same combinatorial expansions. So there are discrete holomorphic functions. And for these functions, what is important is that, okay, on Z2, for instance, or on rhombic timings, you can define function H. Which is the primitive of half primitive. Something like that. I'll give a better definition in a second, which is more adapted to the embeddings case. And then the proof of this statement, it goes by contradiction. You say, I will not be showing you this machinery, but you say assume that there is a sequence of rectangles along which this probability becomes very small. Then, so if you want to prove this, statement, then you say that, okay, assume was not, take a sequence of rectangles with a scale, and then start thinking about the limits of these holomorphic observables. And what will happen is that you will come to the situation when the function H will have in the limit boundary conditions 1, 1 here, 0 here. So if my domains were Dobrushin, by the way, then boundary conditions will be always so here it is exactly 1, here it's exactly 0. This will be approaching 1, and what's important is that this will be also approaching 1. And then there is a way to find a contradiction. In this picture, on the top side. And the origin of this contradiction, I'm just doing this very technical sketch, so it's probably hard to follow, but I'm trying to show you where the origin of the contradiction is. And the origin of the contradiction is that there is a certain positivity of observables on straight cuts using positivity property of F on straight lines, straight boundaries. And positivity simply means that the real part of F, say on this AB, is strictly positive and comparable with F. Why does it help? Because if F is, so let us think about this red cut. So if say is purely real, then when I compute my H, then H has positive derivative along the inward normal. So here, this derivative is positive. However, this cannot hold the same on the top boundary because H is a harmonic function in the limit, and it is already 1. It cannot grow inside the domain. So then there is a complex analysis argument. So you should work here. It's not absolutely straightforward. You should work here. However, this positivity property allows you to find a contradiction. The most technical part is to pass. I mean, this is not a very nice object. You all typically have on the convergence of fermionic observables to the limit inside the domain. So this nearer to boundary analysis is something delicate. However, okay, this works. That's a very, very high level, and of course, they are not very clear presentation of their. So, but my idea was to get to here, is that there are special cuts where you have positivity. So now the special cuts, this is just one of important ingredients. So now there is a notion of special cuts. And by the way, if you're familiar with this definition through interfaces, then all of the stories is about, like, imagine slightly simpler situation when your domain is just a Gaussian. Then if you have a straight boundary and you think about the interface that touches these red points, then the wider number of this interface on the horizontal line is always 0. That's what says that the observables are just real. Okay, so now what I'm saying that there is a replacement of this notion. So in the story of S embeddings, there is a substitute of the notion of straight cuts. And they appeared already in the first paper on S embeddings like 5 years ago. So what is the substitute? The substitute for horizontal and vertical. And this substitute is defined geometrically. You just say, if I have whatever surface, I doubt I will be able to draw a good picture, but at least try. So this is my surface in R21. What I should do, I should cut it by a slope 1 plane. So this guy is a slope 1 plane. Okay. By the way, I didn't mention this, but I mentioned this last week several times. Q as a function of S, this is when you fold the plane, all the distances decrease. So this is a K-Lipschitz function. The graph of this function is K-Lipschitz. So when you cut it by slope 1 plane, you always have something there. And this turns out to be the right substitute along which you have positivity. on this cut, here, this is an S cut. And again, I simply, here, there is no chance to give you, any details on that, but that's a geometric definition. Just cut the surface by this planes. And one side of this cut is good for wire boundary conditions. You have positivity if it is yellow, and the other side of the cut is good for red boundary conditions. And when I say good, I mean that there is a similar positivity phenomenon. This is not terribly simple to see. However, this is an explicit computation. So probably one can work with widened numbers, so I prefer to work in a different formalism. So that's just, computing here. I mean, the underlying reason is that if you are widening numbers person, then all the interfaces, they pass in a certain direction. And why do we need them? Because our tiling is generally not regular in any sense. So you have quads of very different shapes. And it turns out that taking just straight cuts doesn't work. So that's why you need a substitute. So this is a substitute of the cuts. So in particular, if you want to prove usual RSW, then you can do it somewhat in a similar way, just saying that, let me consider, okay, usual RSW for bounded geometries, just consider this as cuts, form these rectangles out of S cuts, and then, or is this two guys, and then proceed. So this can be used, to prove usual RSW as before. For bounded geometries. However, that's not of terrible interest these days, because Remy Mahfouz has a proof of usual RSW under much weaker assumptions, using some technique that modifies the tiling beyond the boundaries, using monotonicity with respect to domains, and modifying domains beyond boundaries, so that to simplify the boundary analysis. So the key is this analytic part near the boundary, which I'm not giving you any detail on. Okay? However, there is the result of Remy Mahfouz. This is just under much weaker assumption. So you don't need bounded geometries there. So right now, it's not still fully conclusive. There is still a technical assumption. This is a minimal technical assumption under which we know how to do discrete complex analysis. But if discrete complex analysis tools are available, then okay, this is done. Okay, so that's a replacement. And now I still have about 5 minutes, or maybe even 6. So now maybe let me say just a couple of words about what you need, what more you need for that. So that's the last part. I think that the definition I can safely erase, or maybe I can safely erase the statements. Visible. Oh, there is an important contribution of discrete complex analysis on S embeddings. So that's the last probably part. And here, as I suspected, I don't have any time to go into the argument of Hugo, Jan, and Van Sant, but that's a kind of a, repeating the same scheme. So what is important? Discrete complex analysis scheme. There are two propositions. So the first proposition is as follows. Assume that we have a domain, say with Dobrosian boundary conditions. One part of the boundary is yellow, the other is red. And this is an S cut. Oh, this is a yellow part of the boundary is this special part on which we have positivity. Now what I'm doing, I'm summing over all boundaries and let it be the length. I'm summing over all boundary points. So this is KB. The probability is that my point X is connected to BA. So the probability, all the events like that. I claim that there is an upper bound, that this guy cannot be. So this is of order square root of R, and this square root, this is one arm exponent of the Ising model, which is 1/2. Okay. So there are roughly R points, and each of these points and the mesh size, or mesh size is 1. Each point contributes 1 over. So for that, I need, well, in full generality, this cannot be true. If the yellow boundary is too close to the red boundary, then these probabilities are huge. So just provided that there is some space. Some space above. Like there is epsilon R space, space there. So this uses positivity. So this is simple. This uses positivity effect. And the fact that you can write this sum of probabilities, that the sum of probabilities is comparable with the integral of f over the boundary. And then you say that you deform the contour. Instead of integrating from A to B over the boundary, you can integrate inside. And then all the a priori estimates coming from discrete analysis will help you to prove that. This is easy. And there is a bit hard proposition 2, which says that actually there is a similar lower bound. With, of course, some different constant. And this is just uniformly over all domains. And actually, what you are proving, you can, I mean, the most conceptual way of saying this is that even if you have this cut with, I mean, even if your domain is the full plane without this cut, the sum of probabilities that it is connected this way is still well, right. So I'm using monotonicity and I'm pushing the yellow boundary as far as I can, and this as far is at most the other side of this. And here, by the way, this technical remark that I made that for this cut, one side is good for one type of boundary conditions, the other side is good for the other boundary conditions, it plays a role. So this is a bit harder. It's harder. Analysis of quasi-analytic functions. Which is a bit interesting because you have to prove a fully probabilistic statement. What we need a uniqueness principle for functions with bounded distortions. Anyways, yeah, that's not an antipode. So that's not an ingredient which is provided by discrete complex analysis. And if you think very broadly about that, what I said that on these special cuts, we have control of the boundary exponent. And then this renormalization argument of these people implies the result. I'm a bit cheated here. This argument actually, in one technical place, uses translational invariance. If you are really familiar with details of this paper, which we do not have in our model, we slightly improved it. So actually, one can. I mean, it's used really in a technical place, but it's a bit annoying. There is a way to get rid. That's just a message, and I don't want to go into any details more because that's already terribly technical, and I apologize for that. But at least on the Blackboard, I hope that still, several pieces are seen simultaneously. It's maybe even a bit better than. Thank you.
Okay, thank you. So are there any questions?
Okay. Okay, I am sort of curious to hear how you get rid of the renormalization step from the DCMT paper, if you could say some words on that.
Get rid of translation invariance.
To the translation. Yeah.
No. Sorry. No. We cannot get rid of that. No. That's the key argument. No, what I'm saying that at a certain point, they use a clever trick. I'm extremely bad with all such tricks. We saw some during the last week, like, take the symmetric copy of this cut or just shift this cut subsum above, or you use symmetries in a clever way. And then all of a sudden you get result out of nothing. So it's a bit annoying that a trick of that kind is used. However, yeah, I just wanted to announce that it's not needed. Though in our situation, we're a bit more flexible because these cuts, they kind of can go in all the directions. Even though that's not a straight line, but we kind of have a flexibility to turn directions. But that's, that's not, this doesn't explain anything. So just.
Can you explain the second picture, the second probability?
Can I explain this part?
No, the second one.
Proposition 2. Wow, that's the hardest part. So how do you prove proposition 2? Very broadly. You just say, okay, let me again assume contrary. Take a subsequence of these domains. Assume that in the limit, after a proper normalization, this actually tends to 0. Then what you will get the following story. And let me just write it as if I were working with the standard square grid case. But I'm trying, that's just to simplify the notation. So assume that we are on the square grid, but I'm telling you an argument which generalizes. Then what do we have? We have a straight cut. Like that. Maybe. we have functions that are just one here, 0 here. And we know that the sum tends to 0. So let me already pass to the limits. So like f delta converges to f, h delta converges to h, and the primitive of f delta converges to some function g. So h is 1, h is 0. Now, from assuming the contrary, what you get that g is constant on AB. So g, which is a holomorphic function, is a constant on the segment. This cannot happen by uniqueness principle. So you do Schwartz reflection and you win. So because of that, you know that f is 0, h is just some constant. And because that's also primitive of the squared. And then contradiction with boundary conditions, h equals 0, h equals 1. Because it would be weird that h is constant because it has different boundary conditions here and there. This step also requires some analysis. Now, what is a problem when the guy is not flat? There is a technical problem here. So I'm using, when I say that my function is constant, and because of that, it should be constant everywhere. But let me introduce one more step, then g is constant. Then. So when I'm saying this, I'm using the boundary uniqueness principle for holomorphic functions. And in my situation, my functions are not holomorphic. There is a certain complex structure behind. So what you need for this passage is that g belongs to W1 to minus epsilon. So if g belongs to W1 to minus epsilon, where epsilon depends on the Lipschitz constant of the surface, this works. And then the whole proof works. And to prove that g belongs to W1 minus epsilon, I'm sorry, but that's long and I'm close there to the end. So this is more or less equivalent to say that f, which is the derivative of g, belongs to A 2 minus epsilon. And what you can do from the a priori regularity theory implies that f blows up at most as a square root. Well, this statement is not, well, it's known. It's a known theorem from geometric function theory. That's not absolutely, I don't know. It's not very well known for those who are not in analysis. Like with W1, 2, everybody knows it with W1 to minus epsilon. You need to be slightly, okay, one tiny more step. I'm sorry, there. I hope this at least told you something, but I cannot hear of others on this.
Okay, so maybe let's keep the rest of the questions for break. Maybe we'll take a 5-minute break and start again at 10:25. Let's thank Dima again.
Thank you.